Hey everyone, today we're going to be testing if the Tesla turbine actually works. Now, normal turbines work by turning a blade that's angled to catch the fluid hitting it. So it comes in at high pressure and leaves at lower pressure. Now, the energy from the change in pressure goes into spinning the blades, but there's also a lot of lost energy. In a modern bladed turbine, about 35% of the energy is lost. This is because there's a lot of swirling fluid moving around in different directions. And whenever you have fluid rubbing against itself or the walls of a container, then you're going to generate some heat. You can see this happen in a blender when you just swirl around water really fast in place. The temperature increases. So the energy that you could have turned into useful work gets wasted as heat. So what could we do about this problem? Well, this is a problem Nikola Tesla set out to solve in 1913 with the patent of the Tesla turbine. The Tesla turbine was unlike any turbine that had ever been produced before. Instead of having blades that the fluid would push against to turn the rotor, he completely removed the blades and had only discs that moved with the fluid. For example, I have a DVD here. Watch what happens when I blow air along the DVD. The disc begins to rotate because of the air moving along the top surface. Whenever fluid moves by a surface, something happens called the no-slip condition. This means that there's a layer of fluid that sticks to the surface of the material. Then there's another layer on top of that that's moving slightly faster, then another layer on top of that that moves a little bit faster. These layers stack up with slightly increasing velocity until the bulk fluid velocity is reached. So you start out at 0 on the surface and then you reach the bulk fluid velocity. The disc is spinning because the momentum of the air that gets stuck in the boundary layer is transferred to the disc. Now, the nice thing about causing a disc to spin like this is there's very little wasted energy because the fluid isn't swirling all over the place, rubbing against each other, creating heat. Especially if the fluid and the disc are moving at close to the same speed. Then the fluid can be in laminar flow and there's no turbulence to heat the fluid up. So we know this seems like a good design so far, but notice how the fluid's only in contact with the disc for a short period of time at the top of the disc here. In order to extract more energy from it, we could make it so that the outlet isn't just right here, but it's at the center of the disc, so the fluid has to travel around the disc in a curved path and then leaves out the center. So the disc would look something like this. And we could put it in a housing that would force the fluid to leave through the center. Then we could just add a bunch more discs with a little space between them that's large enough for the fluid boundary layer to form. Now you have the Tesla turbine. So the air comes in here and goes around the tubes and gets forced out the center here. So in the end, the air is forced to come out this center hole here. I'm going to flow air through it now, but I could also flow water through it technically. On the rotor here, I put a little shiny sticker so I can shine my tachometer on it to see how fast it's actually spinning. The glare here blocked the reading, but it averaged out at around 3,500 RPM. Now technically, if you're in laminar flow with a Tesla turbine, you can reach up to 95% efficiency. Tesla actually built several versions of this, with the largest turbine 15 discs with 60-inch diameters that could spin at 3,600 RPM and generate 670 watts horsepower. So what's the deal? Why aren't we using Tesla turbines everywhere? Well, there are some problems with it. In order for the turbine to reach this efficiency, the discs need to be moving at about the speed of the fluid moving across them in order to be laminar flow. If it isn't laminar flow, then the efficiency is greatly reduced. So that means that the discs need to be spinning extremely fast, or you have to increase the number of discs and decrease the spacing between them. And not only that, any minor imperfections in the discs or around the edges makes the fluid become turbulent, and the efficiency is also greatly decreased. And even if it were perfectly machined, you still get losses when you apply a load to the turbine because it slows the discs down, and when you change the speed of the disc, it changes the number of spirals the fluid makes before it exits. So in practice, you only get around 65% efficiency for a Tesla turbine. So you're right about the same efficiency as a regular turbine. But there are still some advantages to the Tesla turbine. They use discs, which are easy and cheap to produce compared to blades, and the Tesla turbine can also be reversed when needed, unlike a traditional turbine. You can even use Tesla turbines for high viscous fluids and get a high efficiency. Because of the slower flow rates, you don't get as much heat. But still, we don't use Tesla turbines today. This is because unless they're an order of magnitude better than current turbines, there's too much risk and cost associated with replacing all of the turbines that are currently in place in our infrastructure with Tesla turbines. So for now, the Tesla turbine will just remain an interesting way to make a turbine. And thanks for watching another episode of the Action Lab. I hope you enjoyed it. If you did, don't forget to subscribe and check out theactionlab.com for Action Lab gear. And thanks for watching, and we'll see you next time.